Welcome to Math 120. I'm Rashad. Today's lecture is on double integrals. Before we start studying double integrals, let us recall what was the context under which we studied integrals of one variable. Now, if you remember from the first few lectures, integrals of one variable arose naturally while studying the area problem. The area problem is as follows. You have been given a function f of x, which is above the x-axis, and in terms of inequalities, this means that f of x is greater than or equal to 0. And we want to find the area under f of x and above the x-axis in the interval x equals to a to x equals to b. Okay, and in terms of inequalities, this is a is less than or equal to x is less than or equal to b. And you know that the area is simply the definite integral from a to b of f of x dx. And a similar way, the integrals of two variables arise naturally when we study the volume problem. To find the relationship between definite integrals and the area, we used a concept known as the Riemann sums, where we had a function f of x and we constructed n many rectangles to approximate the area. Now, each of these rectangles had equal width. We call that width delta x. All of these rectangles have a width of delta x. To find delta x, all we need to do is to find the entire interval, the entire length interval in the x-axis, which is b minus a. Because we have the rightmost endpoint is b, the leftmost endpoint is a. We divide it equally n many times to find delta x. Now we also want to index the lower left corner of each of these rectangles. So the leftmost corner is called x0, and we know that x0 is nothing but a. To find x1, the next corner towards the right, we just move, starting from x0, we move delta x times towards the right, which is a plus delta x, because x0 is a. And similarly, we can find x2, we start from x1 and move delta x times towards the right. So we know x1 is a plus delta x, which is nothing but a plus delta x, which is nothing but a plus 2 delta x. Similarly, we can find x3. You can work it out. It should be a plus 3 delta x. So on. And you can see that the pattern over here is that you have a plus 0 times delta x, because there is nothing. Here it's 1 times delta x. Here it's 2 times delta x. And for x3 we have 3 times delta x. For xi, we will have a plus I delta x. And the last point will be xn, which will have a plus n times delta x, and this should be equal to b, because we are supposed to end over here. In order to find the height of each of these rectangles, we can consider any point in between each of these line segments. For instance, the first line segment is from x0 and x1. The second one is from x1 to x2, and so on. So we can consider, for instance, for the first rectangle's height, we can take any x point within this line segment and evaluate the value of that function at that point. But for consistency purposes, in this lecture series, we have chosen to consider only the midpoint, and we'll label it as x star. So the first midpoint will be labeled as x1 star, the second one will be labeled as x2 star, and so on. In order to find the midpoint, for instance x1 all we need to do is find the left corner and the right corner, add them up and divide it by 2. For instance, x1 star equals to x naught, the left corner, plus x1, which is the right corner, and then we need to divide it by 2. And from this one you can see that xi star will be equal to xi minus 1 plus xi divided by 2. Let's put 1 here as I. You can see that x1 star will be x1 minus 1 is just 0, so it's x naught plus x1, which is x1 divided by 2. So these two satisfies the lower one satisfies the upper one. Similarly, this formula should be true for all of these midpoints. Now, what is the area of the ith rectangle then? We have the height of the ith rectangle, which is the value of the function evaluated at each of these star points, the ith midpoint, with the width of the rectangle, which is delta x. For all of these rectangles, the width is delta x. And then the area of this entire region should be approximately equal to the sum of the areas of the individual rectangles. And this is equal to sum f of x I. Now I starts from 1, indicating the area of the first rectangle, this one, and as it moves on it will end at n. So we end our summation at n. Let's say we want a better approximation than the summation that we've written over here. What can we do? Well, we can see that if we increase the number of rectangles in this region, the underestimations, like here there's some gaps within the curve that our rectangles did not cover, the underestimations would actually go down, and the overestimations where our rectangles covered some area that was not really under the curve, they will also go down. It means increasing the number of rectangles will actually increase the accuracy of our summation, of our area. And also note that increasing the number of rectangles will decrease the width of each of these rectangles. You can also see this from this formula. Delta of x is b minus a divided by n. Now b minus a is always same. The endpoints do not change as we increase or decrease the number of rectangles. What does change is n. If we increase n, delta of x must go down. So what can we do if we want a better approximation? We increase the number of rectangles, which is the same thing as increasing n. And because delta x is b minus a divided by n, and b minus a does not change, so delta x also decreases as n increases, so it decreases. Now, in order to get the exact area, what we can do is take the limit n approaches infinity. Now, if we use a very large n, our delta x will be really small, right? So, as n goes to infinity, delta of x is really small, and mathematically we call that infinitesimal. We call it infinitesimal. The delta x becomes infinitesimal. And we then label delta x as dx. We also change our sum symbol to an integral symbol, And so the area under f of x is equal to, now the sum being replaced with the integral, then f of, here we had f of x I star, but note that if the width of each of these rectangles are really small, then the midpoints and the endpoints are really close together, as if we only have one point, which is why it will replace xi star with just x, and delta x becomes dx, and the endpoints are just a to b. We knew that before from earlier lectures, that the area under graph must be the definite integral. Similarly, we will now show that the volume under a surface is related with integrals of two variables. Let's look at a few graphs of surfaces. I've taken these graphs from Stewart's calculus book. In this graph, you can see a function f of xy, which is a multivariable function. It depends on both x and y. Our problem is to find the volume underneath this surface and onto this rectangular region given by these bounds on both x and y axis. So in x axis, you can see that the points that we're interested in that belong to these rectangles actually vary from x equals to a. They're either greater than or equal to a, and they have to be smaller than or equal to b. Similarly, in the y-axis, all of these points in this rectangular region must vary from c. They have to be either greater than or equal to c, or smaller than or equal to d. Anything beyond this region is going to lie outside this rectangular region. So these two inequalities give me this rectangle. And to write them in a more convenient way, we often use the interval notation and label our region as R. So in the interval notation, what we do is write the first x point, then the second x point. So this describes only the interval in the x-axis, and we write a cross, and then we write the second interval in the y-axis. It's y1, y2. The first y point, the second y point. Now you can see that the first x point, our first x interval is just from a to b, right? So the first point is a, the second point is b. Similarly, our y interval, y starts from c and then ends at d. Now a common mistake is to mix that up. Do x1, y1 crossed x2, y2, and this is wrong. Do not do this. Okay, so here this graph will actually speak clearer than words what we want to do. So we want to erect rectangular columns from each of the small rectangular regions, and each of these rectangular columns have a specific volume, right? It's the length, width, and the height. And the length and the width gives the base area, which are these smaller rectangular regions, the area of these rectangular regions. To find the height of each of these rectangular columns, what we can do is take any point in this rectangular region and find the value of the function at each of those points. Like this graph here shows how to take them. Like here, this is one of the points, and here this is another in this rectangular region. In each of these rectangular regions, we will take only one point and evaluate the value of the function at that point. Now I prefer taking it in the middle. Then the approximate area is slightly more accurate than taking it randomly or even at the ends in general. Now here the book did not. The book simply took the points randomly, and we'll do an example how to evaluate an area, not an area, the volume in this volume of this rectangular columns, and find the volume underneath the surface as an approximation. And there we'll always take these points as the midpoint of each of these rectangles. Okay, and here you'll note that instead of having only delta x, we have both delta x and delta y. What this means is that we'll kind of like repeat the process for both the x-axis and the y-axis, where in integrals of one variable we only did it for x-axis. So we'll now repeat the same procedure along both x and y-axis. If you remember, we have the interval from a to b along x-axis, and what should we do? The same thing as before. We'll divide it equally in n parts. There should be n many stripes here along the x-axis. Let me just write it down. Similarly, along y-axis, we'll have m stripes. Okay, so this means that since our delta x, all of these lengths are actually equal, right? So delta x is, we take the entire interval starting from b and then ending at a, same thing as before, divided by n. And delta y has the exact same logic, where our interval is from d to c, and we divide it in m steps. Right. Also, we can index them. It's the same with the same logic as before, that x naught starts from a, and then we move one step towards the right by delta x units to get x1, and repeat the process again with delta x units to get x2, and then at the very end we'll have that as we keep on going to the right by delta x units, at the very end we'll get b, which means that this is xn. The nth index should point at the end point. And we'll do the same thing for y. Y naught will point at c, and then we'll move vertically upwards by delta y units to get y1, and we keep doing the same thing and end at ym, which should be at d. And the ith index is just an arbitrary index that can vary from 1 to n. So for instance, here we have seen this is xi and this is xi minus 1. So they're adjacent. Like if I decrease 1, it will go to the left. If I increase 1, which isn't shown here, this is xi plus 1. And this way we can index the strip, index our rectangular region. Now for each of these points, this random points in this diagram, we have to evaluate the value of the function f of xy at each of these xy coordinates. We can label each of these rectangles by a coordinate, since all of these rectangles can be labeled with rij, where I increases towards the right and j increases as we move upwards. So the first rectangle can be labeled by r11. The second rectangle can be labeled by, we moved 1 unit towards the right, that means r2, but we haven't moved in our y index because we have stayed at the same y level. That means r21. Similarly, this is r31, and if now we move 1 unit upwards, we'll get r32, because now the y index, which is j, has increased by 1. Right, and we'll label each of the star points. Star points are the one at which we'll evaluate the value of f of x, y, this function. The star points are those points. So, and here what we'll do is take the indices and plug into both x and y. So this particular index should have the same ij index as 32, as the r region, r32. So it's x star 32 and y star 32. Each of these rectangles rij can be more mathematically stated as the interval, the rectangular interval, which is bounded in the x-axis along xi minus 1, from xi minus 1 till we move 1 unit to the right by delta x, we get xi. And we cross it with the y part of our bound, which is starts from here, which yj minus 1, then it moves up by 1 unit to yj. Now this rectangular region is, we'll call it rij. And the area of all of this rectangular region is nothing but, this is delta x, right? So this is length into width, the area, or width into height, whatever we call it. This is delta y. So on all of these rectangles we'll have same delta x and delta y. All of these rectangles have the same length and width. So the area of each of this region rij or any of this region is nothing but, I just call it length into width. Sorry. And the length is, let's say it's delta x, then the height or the width is delta y. Right. So the base area over here, the base area, that is like the area of a rectangular region, the small base area of each of the smaller rectangles is delta x times delta y. Sorry. Yeah. So now we will look at an actual example of the surface z, which is equal to 16 minus x square minus 2y squared, and three different types of approximations. The first one, we have the smallest values of m and n, and we can see that this is not really very accurate. Like this curve once drawn should be something like this, not the curve, I mean a surface. You can sort of feel that there are lots of underestimations like inside this region, like this holes that are not really covered by your rectangular columns, and there will also be some overestimations, and this one is slightly better, in fact a lot better. There's still some underestimations, but it's not as high. There could also be some overestimations. Here we have doubled the values of m and n, and here we have used a lot of rectangular columns, and we can see that it seems almost as if the entire surface has been covered up, which means this will be more accurate representation of volume than this one. As we move to, and this one is more accurate than this one, so this means that as we move towards the right, we get more accurate volume. Now, what is the volume of each of these rectangular columns? For that, we need the rectangular region rij. We need the base area of this region, and we know that this is delta x times delta y, but for convenience we will write this as delta a, this product. Okay, and and we also need the height of each of these columns. So to find the height, what we did was find the value of the function at the star points xij star and yij star, and the area of ij will call it delta A. Great. So the approximate volume under Z should be the sum of all of these volumes of the rectangular column. So we need two sums here, one for I, one for j. Both of them will start from 1 to indicate the R11 region, and then we will end at Rmn region. So the m was used as the division in the y, the y-axis, and n was used as a division for x-axis. And for each column, this part will remain the same thing. So x star ij and y star ij times delta. Now we have the exact same situation. Like if we want to get the exact volume, we have to increase the values of m and n and to a really large number, right? So we have the same sense as before, that we want to take the limit that both m goes to infinity and n goes to infinity. What would happen if we do that? You can see from this picture that as the m and n both increases, our rectangular region will decrease a lot. These regions will get smaller, and as a result, the area will also get really small. We'll call this area as the infinitesimal area. So delta A will become infinitesimal, and we'll label it as dA. And both of these sums will go to integrals. We'll call this integral. The sum will be denoted as integral. So we have now, and also note that as the rectangular regions get smaller and smaller, the points, as it gets infinitesimally small, really small, there is we can just say that there is one point, and that point is just x and y. There will be no star. So now we have the exact volume as the limit n goes to infinity, m goes to infinity, the sum the value of the functions at each star points times the base area. Okay, so and this is, each of these sums will become one integral, and we'll lose our stars because in this, when we consider the infinitesimal scale, there is just really one point, and our delta A will become dA because it's infinitesimal. And the region of we'll have to declare like what is our limit. Like before we say that the limit of our integration is from A to B, but here it's not so simple. Like there are 4 numbers you need to define the limit. So in this lecture, we'll just call the region R as our limit. R defines the entire rectangle over which the integration is taking place, this entire rectangle. So we'll call that the domain or the region of integration is R.